Hello, I'm Forrest Ward. I'm a physics major, and I'll be showing you the applications of linear algebra in electrical circuits. So first off, just want to say that the concepts and mathematics associated with linear algebra are actually widely used in physics. Scalars, vectors, matrices, tensors, they laid the groundwork for some of the most famous and groundbreaking concepts in physics. Some of these include the infinitesimal Hilbert vector space, Schrodinger's wave function, Heisenberg's matrix mechanics, and along with these mathematical concepts, linear algebra is also used to solve for unknowns in electrical circuits. So it's pretty prevalent in the physics world. Linear algebra, or more specifically matrices, are used to solve systems of equations in simple electrical circuits. Normally we do this to find either the current or voltage through a certain part of the circuit or through a certain resistor. We use physical laws and accepted properties of these electrical circuits to help describe the circuit and to create a system of equations. So before I went any further, I wanted to go ahead and define some terms that are used in the electrical circuit world. These are three components that are really, really important to any circuit or just anything electrical. The first one being current. It's the rate of flow of electrical charge from one place to another. It's normally denoted with an I, and it's measured in amps or amperes. And then there is voltage, and is the difference in electrical potential that makes electrons flow. It's the force that moves the electrons, and it's measured with volts, and you'll see it normally shown with a capital V. And then there is resistance, and is the quantity that measures how the device or material reduces the electric current flow through it. The smaller resistant an object has, the more easily electrons can flow through it, and it's measured with ohms. And then all three of these are related using Ohm's law, which is voltage equals current times resistance, and this law is a fundamental property for any electrical circuit, and it's very important. So we also use Kirchhoff's laws to help describe how sections or smaller parts of a circuit relate to other parts of the circuit as a whole. This one is Kirchhoff's first law, otherwise known as Kirchhoff's current law, and it states that current flowing into a node or junction must be equal to the current flowing out of it. So here we can see that there are three wires. They are connected at a node. I1 and I2 come together at a junction, and the current traveling through the wires of the first wire and the second wire will sum up to equal the total current traveling through the third wire. And that's very important also in any electrical circuit. And then we also have Kirchhoff's voltage law. It's his second law, and it states that the sum of all voltages around any closed loop in a circuit must equal zero. This is a consequence of charge conservation, actually, and also conservation of energy. As charge carriers flow through through a circuit, pass through a component, they either gain or lose electrical energy, depending on the component. The negative of the work done by these electrical forces on a unit of charge which passes through a component is called the voltage across the component. So here we can see that there is a circuit loop, that the negative voltage across each resistor added to the total potential difference supplied by the battery sums to equal zero. So we start with a 6-volt battery, and you can see that we have a 2 ohm resistor and a 1 ohm resistor, and there is a 2 amps of current traveling through the whole thing. So you multiply the 2 times the 2, you get a negative 4 volts, and then a 2 times the 1, and you get a negative 2 volts. And the 6 volts minus 4 volts minus 2 volts equals 0 volts, so it works out. And so now that we've familiarized ourselves with Ohm's law and Kirchhoff's law, we are able to write equations that will allow us to find unknown voltage and current values across multiple resistors and in larger circuits. Once we have our equations, we can then change the notation and place the equations into a matrix form, or an augmented matrix, and then we use simple row reduction to solve for the different current values inside our circuit. So I'm going to work an example for you using matrix notation and Gaussian elimination to solve for current values through a circuit. Hey there, so this is the example that I'll be doing. It's just a simple circuit. We have a 5-volt battery right here, an 8-volt battery, a 2-volt battery, and a bunch of different types of resistors throughout it. And we're going to use Kirchhoff's two laws and Ohm's law to develop some equations to solve for the current traveling through each resistor. And then we're going to set up a matrix, and once we get the variables for each current, well, it's going to give us a lot of information about each resistor and the voltage dissipated and power dissipated and that sort of thing. So first off, the first thing that you really want to do is start off by labeling your currents, like giving each current through each area its own label. So we'll start off on the left over here with this 5-volt battery. We'll call the current traveling this direction, we'll call that I1. And obviously I1 is going to be traveling across this resistor because there's only one way for it to go. There's only one direction. And then I1 is also going to be traveling back into the 5-volt battery, so we'll label that I1 as well. So right here we have a junction, just a simple node, and according to Kirchhoff's first law, the current rule, we know that the current is going to split up right here. So the current traveling this way and the current traveling this way is going to sum up to equal I1. So we'll just go ahead and label this one I2. And we know that this one plus this one equals this one. But we're going to rearrange that a little bit, and we're going to say that I1 minus I2 is traveling this direction. It's just a different way of saying it. You know, what we're ultimately doing is reducing the amount of variables we'll have in our equations, which will make solving it a lot easier. So we'll call this one I3. And again, we have another junction right there. So that means this one plus this one is going to equal that one, but we're going to rearrange it again. We're going to call it I1 minus I2 minus I3 is traveling this way. And it's also traveling this way and this way. So it's the same current traveling this way. And then we have another junction right here. So then we can add up these two currents. So we get I1 minus I2 minus I3 plus I3. So that just gives us I1 minus I2 again. Okay? Now that we've done that, we've labeled each section, we gave each section a current. Next we're going to label each loop. So right here, it's pretty obvious that we have 3 loops. Just go ahead and label them loop A, loop B, call that one loop C. And we know that the sum of the voltages around a loop is going to sum to equal 0. So that's how we're going to build our equations from that rule. So start out with A. So we have a 5-volt battery right there. So that's what we're going off of. And we don't know the voltages around the other batteries, or around the other resistors. So we're going to have to use Ohm's law. So we're going to do the resistance times the current. That's going to equal the voltage, but we'll use the variables for this for the current. So for that one, we have a negative 5 ohm resistor times I1. For this one, we have negative 4 I2, and for this one, we have negative 5 I1. And it's going to sum up to equal 0. And I went ahead and simplified it. Get 10 I1 plus 4 I2 plus 0 I3. We still need to include the I3 because some of our equations are going to have I3 in it, so we still need to include it in there. And this is going to equal 5. So we just rearranged it, and then I multiplied it by a negative. Do the same thing for loop B. For loop B, we have a negative 6 times I1 minus I2. We have a negative 3 times I3. Then we have a plus 8 voltage battery right there. And then since we're going against the current this way, we're going to have a plus 4 I2. Okay? And this is going to equal 0. Okay, and I went ahead and simplified it to 6 I1 minus 10 I2 plus 3 I3 equals 8. Hopefully you can see that in the camera. Okay, perfect. So it equals 8. We're going to do one more time for loop C. So we have negative 8 times I1 minus I2 minus I3. And I used the negative 8, by the way, because we can just add up these two resistors because they're in series instead of parallel. So when two resistors are in series, it's practically just like having one resistor. So we just add them up. So I got negative 8, I1 minus I2 minus I3. And we got a plus 2 volt battery right there. And then again, we're going opposite this direction. So we have a plus 3 I3 equals 0. I went ahead and simplified this one again. And I got 8 I1 minus 8 I2 minus 11 I3 equals 2. Okay, so right here we have our equations. We have 3 unknowns and 3 equations. So what we can do is we can set up a matrix, an augmented matrix, and then we can use Gaussian elimination, and solve for each variable. So we'll go ahead and set up this matrix. So got 10, 4, 0, augmented with 5, 6, negative 10, 3, 8, and then 8, negative 8, negative 11, 2. And I went ahead and row reduced it just for the sake of time. I got 1, 0, 0, 0, 1, 0, 0, 0, 1. And I got 0.62, negative 0.3, and then 0.48. So now that these are our current values, so I1 equals 0.62 amps, I2 equals negative 0.3 amps, then I3 equals 0.48 amps. So now this is really helpful because now we can go back through and we can plug in each value for the current with the resistor, and we can find the voltage dissipated or the voltage used by each resistor. And then once we find the voltage through each resistor, we can use another formula where power equals current times the voltage, and that'll give us the power dissipated by each resistor. And it'll tell us a lot about this circuit, and it'll give us a lot of help if we ever need to add extra components into it. We'll know how much current is going one direction. Yeah, so this is just a much easier way to solve for the current through this simple circuit. So yeah, that's how you use linear algebra with simple electrical circuits.